Hello everybody, welcome back. This is Professor Xiao. The purpose of this video is to help you with a specific homework question. The data set in this video is a little special. It's simulated data, not an imported data. Let's look at the Jupyter Notebook. Based on the simulated data, this is the confusion matrix. Notice that the predicted labels are arranged as columns. The actual labels are arranged as rows. This layout is consistent with the format that I recommend to use in the lecture video as well as in the following videos. Make sure that you stick to these layouts. Here, I simulated the data based on the key values of the confusion matrix so that the confusion matrix will turn out to be exactly the same after the data is simulated. Note that I use a random seed 10 to shuffle the simulated dataset. As for the imported packages, we only need a short list of these because we are only dealing with the datasets and the model evaluation metrics. All of the functions used here to calculate the model evaluation metrics come from the scikit-learn package.metrics submodule. The confusion matrix again. Now let's calculate the specific model evaluation metric. In this demo, I will explain and demonstrate how to evaluate the model performance by using two metrics, FNR and FPR, and compare it with a benchmark model, which we assume to have equal FNR and FPR. Because scikit-learn does not provide a function to calculate FNR, you would have to calculate by hand or use a workaround. If you have calculated TPR, which is recall, then you can make use of that result. Here I'm using the result of TPR or recall calculated in another video. And the relationship between recall, TPR, and FNR is that they add up to 1. Because both are based on the row sum of the first row in the confusion matrix, as shown on the screen. So if you have calculated one of these, you can simply use 1 minus that result to calculate the other. Alternatively, you can calculate FNR by dividing the false negatives by the sum of true positive and false negative. You should get the same result. Here, let me run this code. Scikit-learn doesn't provide a function to calculate the overall error either, but luckily we know that the relationship between overall error and overall accuracy is that they add up to 1. This is pretty straightforward. If you have calculated accuracy, you can use that result to calculate error, as shown here. Alternatively, you can calculate error by using the sum of the two cells on the off-diagonal line and divide that by the total sample sizes. Now let's run this code. And after you have calculated FNR and overall accuracy, and assuming that you also have calculated FPR, which is demonstrated in another video, we can compare the results and make a conclusion about the model evaluation. Here I print the 3 results. I'm seeing that the false negative rate is 0.03, very small. The false positive rate is 0.19, pretty sizable, and the overall error rate is 0.14. You can see that the false negative rate and the false positive rate not close to the overall error rate. This is because the dataset is unbalanced in terms of the two outcome labels, the positive and the negative labels. This often happens in the actual data science projects. You would almost always have one of these errors, false positive or false negative errors, being smaller than the overall error rate and the other error being larger than the error rate. So how do you judge this model? Is the false negative rate severer, in which case this model is doing better than the benchmark model if the two errors were equal? Or is this model with slightly larger FPR worse than the benchmark model? The analysis of the model evaluation based on these metrics will entirely depend on the specific case. Let's assume that the specific case is cancer detection. In the case of cancer detection, false negative error is severer. A false negative error means that an actual cancer patient, without knowing about it, did a diagnosis which returned a negative result. The consequence is that the patient goes unalarmed, could miss a critical time window where the cancer is fully treated. The cancer could go into a later stage without being noticed, and the patient could die. That's why the false negative error is severer than the false positive error. Because the false negative error is severer, having a lower, close to zero false negative rate is desirable for the model. By this analysis, you can conclude that this model, which has a false negative error of 0.03, much smaller than the overall error rate, this model is doing well. This model is much better than the benchmark model, which presumably has an equal FNR and FPR, which will be the same as the overall error rate. So in a nutshell, the conclusion is that this model is much better than a baseline model in this particular case of the cancer detection problem. Keep in mind that when you do your homework, you will face a different problem. So you will have to analyze the specific problem and make a conclusion accordingly. So this concludes the case analysis about the model evaluation. I hope you enjoyed this video. See you next time.